It's been an unusually active period for astronomers and sky enthusiasts alike. Between September 23rd and 28th, 10 newly discovered asteroids slipped silently past Earth, each closer than the Moon. The largest among them measured around 41 meters in diameter, approximately the size of a commercial airliner. Then, on October 1st, another tiny asteroid grazed just 300 kilometers above Antarctica, lower than most satellites orbit. It was detected only hours after it had already flown by. A few days later, another small object, designated 2025 TQ2, only a few meters across, passed over the North Pole at an altitude of roughly 3,000 miles. According to the International Space Safety Agency, ISSA, while these asteroids were small, they traversed regions of space typically occupied by the International Space Station. It served as a reminder of how crowded near-Earth space has become. This recent surge in celestial activity has kept astronomers remarkably busy, tracking new comets, near-Earth asteroids, and even observing the interstellar traveler known as 3I Atlas as it journeyed past Mars. Yet amid all these observations, a few researchers have been quietly following one particular asteroid, a so-called city killer that appears to have changed its path in a surprising way. Once thought to be heading toward Earth, it now seems to be on a collision course with the Moon. This asteroid, named 2024 YR4, has begun to raise serious concern. When astronomers first detected it in December 2024, its orbit immediately caught their attention. Early calculations indicated a 3.1% chance of striking Earth in the year 2032. Though small, that probability was significant enough to demand close observation. Measuring around 55 meters in diameter, the asteroid falls into the city killer class, large enough to release the energy of several megatons if it were ever to impact Earth's surface. Over the following months, as astronomers refined their measurements, the likelihood of Earth impact decreased, and by early 2025, our planet appeared to be in the clear. But then came an unexpected twist. The same updated data showed that while Earth was safe, the Moon might not be. According to current models, 2024 YR4 now has roughly a 4% probability of colliding with the Moon in December 2032. In the field of orbital mechanics, that's a surprisingly high percentage. An asteroid of that size hitting the lunar surface would gouge a crater several hundred meters wide and eject millions of tons of debris into space. Some of that debris could potentially drift toward Earth. Researchers estimate that the flux of small particles in low Earth orbit could temporarily increase by up to 1,000 times. While such a lunar impact wouldn't endanger human cities, it could pose serious risks to satellites, spacecraft, communication systems, and the International Space Station itself. Because of this, planetary defense teams are already simulating potential ways to prevent such an impact. Deflecting asteroids is not a new concept. In 2022, NASA's DART, Double Asteroid Redirection Mission, successfully nudged a small moonlet named Dimorphos out of its orbit. However, that experiment came with some unforeseen consequences. The collision caused a swarm of boulders to be ejected from Dimorphos, far more violently than scientists anticipated, something we'll revisit later. For now, the immediate concern is 2024 YR4. The challenge lies in the fact that scientists do not yet know the asteroid's exact mass, and that uncertainty makes any deflection plan risky. If they underestimate its mass, a planned impact might have little to no effect. If they overestimate it, the deflection could be too strong, potentially redirecting the asteroid onto an unintended path, possibly even toward Earth. If a precise deflection turns out to be unfeasible, then the next option under consideration is destruction. One potential method involves a high-speed kinetic impact, effectively breaking the asteroid apart into smaller, less dangerous fragments. A more controversial approach, however, involves the possible use of a nuclear device. A study published in September 2025 suggested that a 1 megaton nuclear explosion detonated near the asteroid's surface, known as a height of burst detonation, could completely disrupt the asteroid regardless of its exact mass. However, detonating a nuclear weapon in space is not a decision to be made lightly. The last time humanity conducted such a test was in 1962, during the Starfish Prime experiment, which generated artificial radiation belts and disabled several satellites. Any future use of a nuclear option in space would require extraordinary international cooperation and would need to navigate complex legal frameworks, including the Outer Space Treaty, which prohibits the placement of nuclear weapons in orbit. For now, no official plans to use nuclear methods exist, but scientists are using 2024 YR4 as a vital case study, exploring what planetary defense could look like when the threat is not directed at Earth itself, but something in its cosmic neighborhood. Statistically, there remains a 96% chance that the asteroid will miss the Moon entirely, passing harmlessly through the void. Yet that even quiet outcome would yield invaluable lessons: how early we can detect such threats, how swiftly we can coordinate a global response, and how reliable our orbital predictions truly are. And sometimes those lessons emerge in ways no one expects, as demonstrated by NASA's DART mission, which, in attempting to nudge an asteroid gently, ended up scattering hundreds of massive boulders into space. In Michael Crichton's original Jurassic Park, Dr. Ian Malcolm once warned that nature rarely behaves in clean, predictable ways. He divided the world into two types of systems. The first are linear systems, simple and proportional. Imagine driving down a clear highway with cruise control. If you tap the accelerator to increase speed by 10 kilometers per hour, the speedometer rises by exactly 10. The cause and effect follow a neat, straight line. Then there are nonlinear systems, unpredictable and chaotic. Picture a parched forest at the end of a hot summer. One small spark, perhaps from a stray ember, lands on dry grass. Within minutes, flames surge up trees, leap across the canopy, and transform the entire hillside into an uncontrollable inferno. The cause is tiny, the outcome immense. Nonlinear systems magnify small triggers into vast, often unstoppable consequences. Keep that concept in mind because in 2022, humanity conducted a real-world experiment that revealed just how nonlinear space can be. We deliberately struck an asteroid, not to destroy it, not to mine it, but to answer a question that sounded almost like a late-night internet debate. If we punch an asteroid, will it move? The experiment was NASA's DART mission, short for Double Asteroid Redirection Test. Its target was Dimorphos, a tiny moonlet roughly 50 times smaller than Mount Everest, orbiting its larger parent asteroid Didymos, about 11 million kilometers from Earth. The mission was based on straightforward physics. Momentum equals mass times velocity. If you know the spacecraft's mass and its impact speed, you can predict how much push it delivers. Add that to the asteroid and you can calculate how much faster it should orbit its parent body. Scientists estimated that the impact would shorten Dimorphos's orbital period by roughly 73 seconds. What actually happened stunned everyone. When DART slammed head-on into Dimorphos, the moonlet's orbit shortened not by 73 seconds, but by 33 minutes. That's a change 25 times larger than expected. At first, it seemed like a victory, a huge success for planetary defense. But as is often the case, the universe rarely plays by our expectations. 2 years later, astronomers analyzing the aftermath realized that shifting the orbit was only the beginning. Something far more dramatic had occurred. We hadn't just moved an asteroid, we had unleashed a storm of boulders. Images captured by LichioCube, a small probe trailing behind DART, revealed the scene just minutes after the collision. Instead of a smooth cone of dust, astronomers saw a chaotic halo of over 100 large rocks, some as small as loaves of bread, others the size of compact cars. These weren't drifting lazily away. Many were hurtling through space at speeds over 50 meters per second. When researchers reconstructed their trajectories, they found that this debris carried nearly 3 times the momentum of the DART spacecraft itself. That was never part of the plan. The concept behind a kinetic impactor is simple. Strike the asteroid hard enough and it moves because of the direct energy transfer. But in this case, the ejected material, the boulders and debris, added an unexpected secondary boost, amplifying the total effect. Essentially, the impact became a 2-stage event, the initial collision followed by a violent explosion of rock fragments. Even more intriguingly, these boulders weren't scattered randomly. They appeared in 2 distinct clusters, with clear gaps between them, suggesting that some unknown mechanism influenced their ejection pattern. Researchers are still analyzing this strange distribution, working to understand what happened during those crucial seconds. Their findings will be essential for future planetary defense missions, providing real data on what happens when theory meets the raw unpredictability of space. This wasn't the first time unexpected details emerged from DART's aftermath. In April 2024, scientists reported that some of the largest ejected boulders could be on long-term trajectories toward Mars, potentially colliding with the planet in about 6,000 years. A fascinating yet sobering thought, especially for any future human colonies that might one day live there. Then, in August 2024, new simulations using data from LichioCube suggested that a few smaller fragments might eventually reach Earth in roughly 30 years, possibly producing a brilliant meteor shower, though not a dangerous one. While DART proved that we can indeed redirect an asteroid, it also revealed how complex and messy the real physics can become once we step beyond equations and into the cosmos. Asteroids aren't smooth billiard balls. They're irregular, fractured, and unpredictable, filled with dust, rock, and mystery. That's why ESA's upcoming Hera mission is so important. Hera is a follow-up spacecraft currently en route to the Dimorphos system, expected to arrive in late 2026. Unlike DART, which was designed to hit and observe from afar, Hera's role is to stay, to survey the impact site in detail, map the crater, analyze the debris field, and measure how the asteroid's orbit and structure evolved over time. Hera will provide the crucial ground truth, verifying the predictions made by the DART and LichioCube teams and helping scientists refine the models that simulate asteroid impacts. It will determine whether the ejected debris behaved as expected or continued to act in surprising ways long after the initial strike. This mission is vital because effective planetary defense relies on accurate data. We can't depend on a single experiment to represent how all asteroids behave. Some are dusty, others icy, and many are covered in massive irregular boulders. Each type poses unique challenges. Understanding those differences and preparing for them could one day determine how well humanity can protect itself, its satellites, and even its celestial neighbor, the Moon, from the unpredictable forces of our cosmic environment.